back to the CCENT journey with me, Ryan. In this next section, we're going to start looking at NAT, the Network Address Translation, and this is part 4 of the CCENT, the Infrastructure Services. For those who don't know, you can contact me here on YouTube, on LinkedIn, or Twitter. So NAT, Network Address Translation. Why NAT? The main driver behind NAT was one simple goal. It was to conserve and to slow down the use of public address space. Now, previously, what we would normally have had is a building. Let's say we had 5 devices in that building. That building would connect to a router that would give them some sort of internet connectivity. And what you would normally do is assign a public IP to each one of those devices. But nowadays, as we know, even our homes have a lot of devices, and it's just not viable to assign each device its own public address. So we had to come up with this way to try and mitigate against that by using less public IP addressing and relying more heavily on the RFC 1918 private IP space. So what we done was we had 10 devices on site, and these would actually all individually get a private IP address, and then normally your ISP would give you one public address, and the router would actually run the process of NAT, the network address translation, and as traffic comes into the device wanting to go onto the internet, it would perform NAT, and it would use a single public IP for all the devices and services on the internet to communicate back with. So you could take as many devices, well, to an extent, on site and push them through a single public IP, as opposed of giving them all individual public IPs. This is why we use the RFC 1918, very important number to remember. And this is the private IP space that we spoke about in the past. So the main driver behind that, like I said, was the conservation of it. It was designed as a temporary solution for IPv4. The permanent solution is to get rid of IPv4 and move to IPv6. So unlike IPv4, which has 32 bits available, with IPv6, we actually have 128 bits available. So NAT is used to separate the private LAN and public WAN. So it's very similar to what we just seen then. The idea again being is your NAT device, and I say NAT device because NAT is not always performed on a router. NAT is, I would say in my experience, primarily performed on a firewall at the edge of the network, but that will depend on where you sit. So for example, in most of kind of what I do as a role, as a job, I normally have a edge device like a firewall, and that sits on the edge of a MPLS network. And the way this works is every device, including the routers, and then down here are sort of sites, and every device behind the firewall is private, and up here is all public. And again, normally we have a range of public addresses. Let's say, for example, we give the customer a /29, so they have 6 usable IP addresses and they're all public. But inside this MPLS network, they literally have tens of thousands of devices using that private IP space, the 1918 space, at each individual site. Even the routers themselves on both this interface and this interface is all private, and all the devices inside the MPLS core is again private. What you may see as you kind of enter into the networking world is you may see kind of the internet, and different ISPs to different sites. And just like your home connection, in a sense, is you're going to have devices connecting off the back here, and it might be the router itself at each site that performs the network address translation, where you would have anything here would be public, so same is true over here, and anything behind the router would be private. So the separation between public and private is where NAT occurs, and NAT can occur on multiple different devices. Now, it can occur on primarily routers and firewalls. That's where you primarily see it, but I have also seen it on devices like load balancers, which is obviously outside of the scope of the CCENT, and I've even seen some makes and models of switches that are kind of layer 3 or layer 4 switches also perform NAT, network address translation. So it kind of goes back to a separation of where does that public and private meet and what device is performing the NAT. Don't always expect it to be the same device in different networks, because it's not always the case. But normally at a CCENT level and at a CCENT job role, I would expect to see 90% of any NAT boxes or any devices performing NAT to be most likely routers as opposed to firewalls. Security. NAT offers us some security depending on the NAT type that we're using. We'll start to find out there are different types of NAT, like static, dynamic, and so forth. But the one I'm particularly talking about here is something called PAT, which is Port Address Translation. And this is arguably the most common NAT that we use today. And the idea behind it is, as a device goes out onto the internet, let's say we have a PC, that PC connects to somewhere out on the internet, and it wants to communicate out. Well, when it does that and the router performs NAT, it creates what we call a translation. And that translation is kind of like an open session in the router, which allows only the response to come back in, and only the response can go down that open session. So the idea is you've got a PC over here and it's on a private IP address, and someone is trying to attack it on the internet. Well, it won't work, because it will hit the front door of the router where the public IP is, and there'd be no open session in order for the router to move it towards that PC. So through the translation that's happening inside the router or firewall that's performing NAT, it in turn offers some basic level of security by only allowing through the response to the translations that were originally sent by a host inside the network. Now, the reason I say it depends on the type of NAT is because there are other types, such as static NAT. And static NAT doesn't create these translations in what we call a translation table. Instead, what static NAT does is a one-to-one translation. So previously, in the examples given so far, I've said that we had 10 private addresses, and those 10 private addresses can use one public address. Well, in one-to-one is kind of what you would expect. We have one private and we have one public, and anything that comes in on this interface that's destined for that public address, it will get pushed through the NAT process and be changed to this private address. And because of that, the NAT doesn't keep track of the translations or the sessions that are happening on the device, and as such, any traffic that goes towards this interface will just be blindly punted to the private equivalent on the other side of the router, and that's a static translation. We'll get into the different types of translation as we continue through the videos, and we'll set them up in Packet Tracer, but this type of NAT doesn't offer us as much security as things like PAT, which is based on the translation. So what I mean by that again is if we had another private IP and that private IP wanted to use the same public IP address, then we need some sort of method to track the sessions. So to make sure that if one private IP address asks for Google's website, it doesn't then get sent to the different or the wrong host inside the network. And that's pretty much done on the port numbers at layer 4. Remember we talked about those ephemeral ports and the destination ports, the well-known port numbers and so forth. Well, NAT hijacks that concept and uses it to build a translation table that we will see when we set up in Packet Tracer. So security is a important element of NAT. It's not the primary reason for its existence. Remember, the reason is the conservation, and this is again going to be solved hopefully by IPv6. And the security is just a additional benefit that comes along depending on which type of NAT you've set up and how you set that NAT up. So again, like I said, there are different types of NAT. There are source NAT, where we change just the source of the IP address. There's destination NAT, there's static NAT, dynamic NAT, and there's also port address translation, which is PAT, or sometimes referred to as overload. Now if we go and have a look at the Cisco website and go into the infrastructure services, we can see that NAT is listed just down the bottom here, and we need to be able to configure, verify and troubleshoot the inside source NAT. So we need to be able to configure static NAT, a pool of IP addresses for them to NAT against, and again PAT. So there isn't too much to do with NAT inside the CCENT, but NAT is something that is overlooked in my opinion, and it needs to have a bit more focused because the relevance of it inside a real world actual deployment, it's quite significant in my opinion, and it's also where a lot of problems tend to occur, primarily due to the misconfiguration of NAT, because NAT has a few more components with it, and it's important to understand the process that the device, like the router, goes through as the traffic is received inbound and translated outbound. Okay, so I've put together a diagram here, and this will be the network that we work on over the upcoming videos. This is going to be for static NAT. So static NAT is the 1-to-1 translation. And just going over this diagram in a bit of detail, you can see to the right hand side we have public space, and to the left hand side we have private space. In the middle we have the router performing NAT. Now one thing you will notice is the public addresses in this case are actually a private address. And that's not really too much of an issue because routers don't know the difference between public and private addresses. So this could be any address we want it to be, but for this purpose in this demonstration, I've given it a private IP range. Let's pretend that's a public range that's been given to you by your ISP, and your ISP's giving you some sort of internet connectivity. Over to the left, you've decided to use a /24 subnet range. It's the 192.168.0.0/24, and you've given .1 to this PC, .2 to this PC, and let's say .10 to the default gateway, which is going to be the gig 00 that both these PCs will send traffic towards in order to get to internet-based services. What's going to happen is the PC will realize that it needs to speak to some sort of service out onto the internet, and therefore it will realize that the destination, let's say 1.2.3.4, is not on the local subnet, and it does that binary AND calculation to realize it's not in that /24 network, and because of that it sends it towards the default gateway, which in this case is that .10, which is the gig 00 of the router performing NAT. The router receives the frame on gig 00 and it goes through the NAT process. The NAT process changes the layer 3 header from the original source of 192.168.0.0, 01 or 02, and changes it to the public, which is the 172.16.0.1 IP on this interface, and sends it onto the final destination. When the final destination receives that packet, it sends the response back to the public IP of gig 01, which would be the 172.16.0.1. As that's decapsulated, it's sent back down to the NAT process. The source is changed back to the relevant host, whether that's the 192.168.0.1 or 02, and sent to the final destination. Now, one of the limitations we can already see with the design relates to how many IP addresses we actually have. So you can see static NAT is 121. So we need, in this case, 2 PCs to use static NAT. We need 2 public addresses. But if you look at what's happened over here, our ISP is sure enough given us a /30, which we know are 4 IPs, 2 usable. But notice one of the usable is actually assigned to the ISP's router, and therefore we're only really left with 1 usable IP. So in this case, we're going to have some sort of limitation where potentially only one of these routers are able to get to the internet, and the other router is not able to perform any sort of static NAT translation. But what we'll do is we'll go through the configuration. I'll go ahead and configure the PCs and the interfaces on the routers and leave everything but static NAT configured. And then over here, I'll create some loopback addresses on router 1 to simulate some internet services. And then we will see how the router does the NAT and how it responds. Once we understand static NAT in a bit of detail, we'll then start looking at dynamic NAT, and we'll start to investigate PAT. The configurations are similar, but it's important that you understand the differences, both why they're different, as in what situation would you use different types of NAT, and also the configuration and verification of each type. I've said it before that the configuration of NAT is a little bit long-winded, but long as you understand what you're trying to achieve, the configuration does make a bit more sense. There are topics in some configuration for NAT, like ACLs, Access Controls List, which are things that we've not talked about in too much depth, but I'll give an overview before we dive into the configuration of that, and then there'll be later videos picking up Access Control List in more detail later. So that's all we've got time for in this lesson. Let's just go over what we learned. We now know NAT stands for Network Address Translation, and we also understand that it's a temporary solution designed to conserve the IPv4 public address space. So the idea being is previously, before NAT, every device that needed access to the network or access to the internet would have a public IP address, but of course that isn't going to scale very well. So NAT came out in an attempt, a successful attempt, to limit the amount of public IPs required against particular devices. So 9 out of 10 of you watching the video will have a single public address at home in your house assigned to you, maybe dynamic or static from an ISP, and you would have 10 devices or so that are connected to a router or switch, wireless or wired, or receive a private IP, and then that IP address is then actually translated to the single public IP address through the translation and session table. We learned there are different types of NAT. We got NAT such as static, which is what we went over in a bit of detail, and we also have things like PAT, the port address translation, and dynamic. So we jumped onto the Cisco website and we reviewed what's actually part of the official blueprint, and we're going to go through the configuration, verification of each type of NAT. We then finished off by looking at a network topology review. I've gone on to Packet Tracer and I've built a network and I've given it IPs, and what we're going to do in the next video is actually design and deploy a static NAT solution. We're going to ensure that some of our host is able to go out to public services on the internet and how that configuration will look on the router. We then need to look at the limitations with static and why it may be favored alongside PAT. So for example, you may have a PAT solution, but a particular inside address or particular inside host requires its own public address. So you can use both static and PAT in conjunction with one another. Now, NAT is a very detailed process and can get a little bit complicated. Probably one of the most complicated protocols at the CCENT to an extent. And it's important that we stay on track and we don't dive off and look at other things when we're talking about NAT. So I hope that's been informative, and I'd like to thank you for viewing, and if it has been, please do like and subscribe.